Good morning. We're doing some algebra outside today, and we're going to continue with our analysis on quadratic equations and functions. So specifically today, we're going to look at quadratic functions. We're going to look at some analysis of some of their special properties, and look at how we use those tools for graphing. So some quick ideas here is quadratic functions or equations can be expressed in two different formats. They can be expressed in two different main formats. I should say two different main formats that have two variables. So they have the ordered pairs, which are the variables that correlate to the variables of the quadratic equation or functions. Have the ordered pairs x, comma, y, or if it's a function, we'll say x, comma, f of x, where instead of having a y, we replace it with the function format f of x. And we'll be looking at just the quadratic functions today. So for every x and y ordered pair that we have. Okay? So we have equations that are expressed in two formats, and we're going to have two variables that we're going to work with. So when you say it's a quadratic function, you automatically are looking at two different variables, the x and the y, or the x and the f of x, when you want to specify it's a function. Okay, really important. And these two main formats are going to be, number one, we're already used to this format. We've used it when we were solving the quadratic equation, but we are only using it when we had one variable. This is your y, or f of x equals ax squared plus bx plus c format. Okay, and this is your standard or general form. And what's handy about this format is it's used a lot when you have to find intercepts, when you have to use a quadratic equation, and sometimes it's easy when you're just looking at simple things like the opening of the quadratic function as far as the graph is concerned, and some other small little properties. So here's your main format. This is standard or general form, and two is what we call, back up, and say y or f of x equals a x minus h squared plus k format. This format we're going to use a lot more when it comes to graphing. So this is useful for graphing. And the typical label for this format is vertex form. And so we'll explain shortly what the vertex is. So this is your vertex form, where what's visible here is this h and k value. This h and this k value correlate to an ordered pair that is the vertex, the opening of your quadratic function, which is a graph of a parabola. So the opening of the parabola, where HK is your vertex. Okay, we're going to look at what the vertex means. So we're going to look at some of the properties of quadratic functions. So we're going to get used to rewriting it back and forth depending upon what we want to do. And these are the main formats we're going to work with. Okay, next. Our next step is to look at some of the properties of quadratic functions. Okay, we're going to do a little summary first. So here's a summary of the main properties, or sometimes I like to use the word behavior, of quadratic functions. Okay, some of these main properties. So to start with some of the basics, we want to think about what the graph looks like. Graphs of, and I'll just say quadratic functions for short. So quad means quadratic. Functions are what we call parabolas. And what a parabola looks like in a nutshell is an umbrella shape. It's a U shape upwards. So it's a U shape upwards and it's umbrella shape downwards. So what we have is a typical graph that looks like this or like this. And depending upon our function, we can widen the parabola or we can narrow it. We can flip it upside down and we can move it up, down, left, or right. So we're going to look at some of those unique properties and behaviors based on the function equation that we have. So when we look at the function, we want to get a sense of what that parabola is doing. Okay, so these have openings. These parabolas open up or down. That's called the opening. They have a maximum and a minimum value, which we use for a lot of analysis. So if you roll a ball up in the air and it comes down, it reaches a maximum height. So parabolas have maximums, which I'm going to call max for short, or you could only have one or the other, or minimums. Okay, so that's the maximum height it reaches. And the other main property we have is they always have an opening point called the vertex. Parabolas have opening points called your vertex. Which is your HK value that we showed in the earlier format. Okay, so they have an opening point. So this opening point would be here or here. This is your vertex. And if you notice here, this is a minimum. And this right here is also a maximum. So when it opens downward, you have a maximum. When it opens upward, you have a minimum. But be aware, we're going to stress this when we look at analyzing these a little bit more, that the maximum and the minimum, these are the y values. Only it talks about the height, how high your minimum or your maximum are, what the y values are. Okay, so very important. Parabolas also have an axis of symmetry. So they have something called an axis of symmetry. And this is a really neat feature because it talks about the symmetry of a parabola. It's when you splice it up in half, you could fold it into two equal halves. So if you know a point on one side of the parabola, you could find the point on the other side. So an axis of symmetry splits it in equal halves. So, for instance, you could have a parabola like this. Okay, here's my x-axis, here's my y-axis, and what I would do is I would show that this parabola is split right down the center in half. So if I have a point on this side, I'll have a point on this side. So if this is positive x, then this would be minus x. So if I fold along that axis of symmetry, I get the same image on both sides. Very important detail. Okay, so again, this is your min, your max, and your vertex is h comma k. Your min is k, and your max is k. Okay, just highlighting some details here. So these are some of the main features that we can see in the graph. Now, other properties that will come up are looking for your domains of parabola, what are all the possible x values, your range values, and then looking for your intercepts, your x-intercepts and your y-intercepts. So domains of quadratic functions of parabolas / quadratic functions are all real numbers So I'm going to go ahead and put the symbol for real numbers in there. This is our symbol that we use. Okay, so that's always the case when they're quadratic functions. And then the range values, ranges of parabolas, quadratic functions, I'll use my short form here, are depend on your max / min value. So they will go up. If it's a minimum, it will go from that minimum value upwards. If it's a maximum, it'll go from the maximum value downwards. So we'll analyze that a little bit more in detail with some examples. Okay, so we have domains, we have ranges, and we have openings. We have maximums or minimums, and we have a vertex, and we have an axis of symmetry. Okay, what's left? What are some of the other main features? Well, intercepts. Okay, so a parabola or quadratic function is interesting in that you could have x-intercepts, but sometimes you don't. You could have your x-intercepts, your possible x-intercepts are 2 or 1, okay, or none. So let me explain this for a minute. So your x-intercepts depends upon whether the solutions for your quadratic formula for which you're finding these intercepts are going to be 2 real solutions, 1 real solution, or 2 complex solutions. If they're complex, there are no x-intercepts. So what you have to note is that your x-intercepts, or x-intercept for short, are your real solutions. To your quadratic equation, to your quadratic when you set y equal to 0. So they can only be the real solutions. Very, very important fact. And then we have only one other property we want to cover. And I'm running out of room, so I'm going to write it right up here. I only have one whiteboard out here, and one other type of intercept we have is our y-intercept. Y-intercept, we always have one y-intercept from setting x equal to 0. So there'll always be at least one crossing somewhere on the y-axis for your parabola. So those, say, are our main properties. Okay, those are what we're going to look at when we analyze some of these quadratics. So let's go on to our next step and explain these. And give you some examples. All right. It's a good day to do algebra amongst the trees. So let's talk about how we could find our opening without even having to graph it. I'll do both. It's always a good idea when you have a quadratic function to graph it as well, because the graph always is the same thing as the function. It's just the pictorial way of looking at your function. Okay, so let's take a look at our properties in detail. So we're going to call that first property we talked about the opening. Okay. And we have two choices. You open up or you open down. So opens up when the A is positive. So when A is greater than, when A is positive. I will just say that in the ax squared plus bx plus c equals f of x format. Okay, so as long as this a value is positive in front of the x squared, when it's in your standard form, you'll always know that your parabola opens up. And opens up, I always tell students they could just draw a little U shape to indicate it's opening up. Okay, so this is what we mean by opening upwards. Now our other option is, or it opens down. So a parabola will open downward when A is negative. So we have when A is positive, we have an upward opening. And when A is negative, we have a downward opening. So here's some examples. of the following. Quadratics. So number one, I'm going to have a quadratic equation, which is also a function in this case, again. That is, let's say, 2x squared minus 1. Okay? So the first thing you want to check, is it in standard form? Yes, it is. And can you identify your a correctly? Yes. So here you would say, since a is equal to positive 2, we know this opens up. We're expecting a parabola that will be opening upward this way. Okay, now there's some other features involved here, and we'll take a look at those shortly. Okay, number two, if we had a parabola that was, let's say, 2 minus 4x plus 3x squared. We have another quadratic function because it's a function that has an x squared in it. It's in the ax squared plus bx plus c format. Almost, but we could put it in the ax squared plus bx plus c format. So what we want to do is, once we have it in that format, identify our a value and look at our opening. So in our standard form, if I do some rearranging, this will be 3x squared minus 4x plus 2. And I want to identify my a value, which is this number right here. And here, a is equal to positive 3. Okay, so in this case, this opens up as well. Okay. Now, what would I need to do to make this open downward? Well, part 3 here, let's say instead I had 2 minus 4x minus 3x squared. Okay, if I go ahead and change one sign in here, I could go ahead and change the behavior. So this opens up this way, but in this case right here, when I rearrange this, I get f of x equals minus 3x squared minus 4x plus 2, and I can see that my a value now is negative 3, which indicates it gives you an umbrella shape. So this opens down, which you could again indicate by a little symbol, an umbrella shape, a parabola that opens down. Okay, so not much to the opening. Our next step is to look at some other features. What we want to do next is look at a very important property called a vertex. So now, so the vertex, very important. This is the opening point. So opening point are points on any graph expressed in two variables, x and y, are going to be expressed as the ordered pair x comma y, or since it's a function, x comma f of x. So the opening point of the parabola, which typically is expressed as x comma h comma k, as indicated earlier. So I was getting a little ahead of myself. So h comma k is our point that we used to specially notate the opening point of our parabola, which is called the vertex. Okay, and what's going to happen is this point, there's two main ways to find these. And we're going to look at these two ways. And one is if we use vertex form, we identify. And number two is by formula. Okay, so we'll first look at quadratics that are in vertex form and identify the vertex when it's in vertex form. Okay. So let's take a look at some examples here. Finding the vertex examples. Okay, so let me back up. Finding the vertex. Before we get to examples, I do need to highlight a little bit more. So number one, applying using vertex form. Using vertex form, which is f of x equals a x minus h squared plus k. What we want to do is we want to identify the h and the k. And what you want to note is note the sign. You always have to have a minus here, and h is going to be whatever needs to occur to make this a negative in front. So sometimes you might have x plus 3, which means the h would have to be a negative 3. So we'll look at some of those examples. So using vertex form, all we have to do is identify the h and k. So now we're ready for an example. Here's an example. And this would be find the vertex for the function. Let's say we had f of x equals x minus 2 squared plus 3. Okay. This is a quadratic. You can multiply it all out and you can put in standard form. In this case, I don't want to do that if I'm going to just want to find the vertex, because here I could identify this as being my h and this being my k. So if I translate this to vertex form, this is x minus positive 2 plus 3, and this is quantity squared. So this must be a positive 2 to keep the sign minus for the h and the, between the h and the x. So my vertex here, the opening point is going to be 2, 3. It's that simple when it's in vertex form. So notice how it is in vertex form. Here you could also identify what your a is. So just note that your a value is positive 1. So in addition to knowing my vertex, I also know that it's going to open upward. A little side note here. Because we didn't get any examples where you had parentheses involved. So your a value is right here. Okay, next, let's go ahead and look at another example. That would be number 1. So a second example would be, let's see, Here I have another quadratic function. If I multiply this all out, and simplify, I could go ahead and put this in standard form. But since again, I'm just finding the vertex, I just want to keep it in this vertex form. So I could see it's in vertex form. So here, I'm going to go ahead and identify my H. So here's H, here's K. Now the K sign value I could read right off, but what I have to notice here is that my H value is a little off. So this is minus H. So what I'm going to have to do is manipulate this just a little bit so I have it exactly in vertex form. So I write this as x minus 2 quantity squared minus 5. So if you notice, I have to get this minus sign into H. So now this is my H value, and this is my K value. Really important detail, because you have to have this minus sign here in order for it to be in vertex form and identify your H correctly. So really important fact there. So now I could go ahead and write what my vertex is. So my vertex here is minus 2, minus 5. And I can look at this and I can see also, a little side note, that my A value is equal to 2, which is a positive 2. I'll just emphasize that positive, even though it's understood positive. We just write the number, so we know it opens upward. Okay. So a quick little sketch on this. And this is what's so helpful in identifying your vertex. So you could sketch this right away. So we already have minus 2 here on the x-axis, and we go down 5 units. And then this opens up. We're already getting a sense of what that quadratic's doing. A very, very important idea there. Okay. Next step, let's go ahead and take a look at how to find the vertex using our other method. So the second method, number 2, is finding the vertex using your formula. Okay. So here what we do is we make sure that we have standard form. So sometimes you might be giving a quadratic in standard form already, and you can use the A, B values that you have to find the vertex. So when you have your quadratic in standard form, then the x value of the vertex is x, which equals your h value, is always going to be negative b over 2a, and the y value will be will be equal to k, which is equal to f of negative b over 2a. So the y value of the vertex is whatever you get for your x, and you plug back into your function and get an output. That's going to be your y value of the vertex, where h comma k is equal to negative b over 2a comma f of negative b over 2a. Okay, so this is the formula we use. So what you have to do is be able to find your x value using negative b over 2a from your standard form, which again is ax squared plus bx plus c. And then you plug that function value in to get your y value, and you have your vertex. So if you're into memorizing formulas, there's one for you to know, and you can use when you have it in standard form. So let's look at a quick few examples. So some examples. Number one, find, I'll add that after, find the vertex of the following. Quadratics. So number one we'll have f of x is equal to negative x squared plus 4x minus 3. And to do this, what I'm going to do is first see if it's in standard form. So it is in standard form. And I need my A and B values. So what I want to do is in standard form already. So the easiest method really is to identify what my A and B are. So since I know that A is equal to negative 1, which means this is going to be a downwards parabola. A is equal to negative 1 and B equals 4. Then what happens? Or we know 4 equals 4, but here B equals 4. So since A is negative 1 and B equals 4, then according to my formula, the x, or the x value of the vertex, which is also known as h, will equal negative b over 2a, which in this case will be negative 4 over 2 times negative 1, which breaks down to negative 4 over negative 2, which breaks down to x, or h, equals 2. So I have the x value of the vertex. The next step is to plug that 2 into my x values and find the output, which would be the y value of the vertex. So now the y, which is equal to the k value, will equal f of negative b over 2a. So here we want to find out what f of positive 2 is. Excuse me. Here, since I'm going to rewrite my function so I don't make any mistakes substituting, f of x equals minus x squared plus 4x minus 3, then f of negative b over 2a here, which would be f of 2, will equal the opposite of that 2 squared plus 4 times 2 minus 3, which will be equal to opposite of 4 plus 8 minus 3, which equals 4 minus 3, which would be 1. Okay, so I get k is equal to 1. Thus, the vertex hk is going to be 2, 1. So that's the opening point for this parabola. So if you notice, A is equal to -1, so it opens down. If you were to do a rough sketch, you'd say, okay, well, 2, 1, just to get a sense of what this quadratic function or parabola is doing. You could see that 2, 1, according to my scale, is approximately right here. And then this opens downward, and it'll probably have something that crosses. It'll cross the x-axis in 2 places, which will be the x-intercepts. So that just gives me a little rough sketch, okay, of what's going on. Yeah, that's how you use the formula to do this. I think we're good with one example there, because I want to move on to the axis of symmetry and give us some examples where we're doing a lot of full analysis. Okay. Let's go ahead and look at the axis of symmetry. I have a very happy bird in the background. You must like quadratic equations. So our students for today that are visibly in the classroom. Okay, so the next big property is the axis of symmetry. And we love symmetry in mathematics, or in general anywhere, especially in physics, because we know it has certain properties. If it has symmetric properties, there's a lot we could apply to understanding the equations at hand. Okay, the axis of symmetry, it's a vertical line. It's a vertical dotted line through the x value, or rather h, of the vertex. Okay. So if we take our parabola and we slice it in half right through the vertex, that is our axis of symmetry. So this is always your axis of symmetry is always x equal to 8. Okay. So it's always going to be x equal to h. So what you need is you need this value from your vertex. It relies on the x value of your vertex. At least you need the x value of your vertex to identify that. Okay. So here is the illustration. And I'm just going to draw a sketch. So that would be my vertex right here. This is h comma k. And you might notice there's some symmetry. If I know that I have this point at 1, let's say, then by the fact of the symmetric properties of this parabola, quadratic functions, I know on the opposite side I have the exact same point. Y value at 3, 1. So the idea is your axis of symmetry is this dotted line right through the vertex. So this is your axis of symmetry. and some people call this AOS, axis of symmetry for short, if you don't like writing too much. And this axis of symmetry is this dotted vertical line that splits it into two halves. So if you notice, if you fold this over, you get the same image on both sides. And the axis of symmetry here, I need to state as a vertical line, and vertical lines are always stated as x equals some number. So here we have x equals h, which means that all your x values are, in this case 2, or whatever the h value is here. Very important detail. So that's what your axis of symmetry is. And next we're going to look at min or max values, minimums, and maximums. I'm going to say slash. I'm running out of green markers here. So minimums and maximums, every quadratic, that one's better, every quadratic function has either a minimum, which we're going to denote by min, or a maximum. Max. Okay. You're going to have one or the other, but not both. So, what happens is if it opens up, if your quadratic opens up, then let's think about this. Then you're going to have a minimum. Okay, then you have a minimum in capital letters. So opens up, you have a minimum value. So it could be the lowest point of your valley. So if you think about how, mountain ranges and valleys work, it's the lowest elevation point there. Okay. If your quadratic opens down, then you have a maximum. Okay, so opening downward yields a maximum. So downward would look like this. And this would be your maximum value. Your minimum value. So it would be like the highest peak of a mountain. If you throw a ball up in the air, or don't typically like to throw things, I'll throw this marker so I don't use it again. I throw this up, it goes up, reaches a peak and comes back down. That's your maximum. Okay, so you can either have it open up or down. Now, the important thing here with minimums and maximums, these are always equal to the y value, or what we call k, the y value of the vertex which is your k value. Okay? It's always the y value. This is a point that I think a lot of students get confused with. The y value expresses how high or how low something is. So it's only the y value of your vertex. So it's y equals k. Okay? And it could be positive even when it's a minimum. It's just saying that's the lowest point of your entire graph. So let's take a look at some examples here. So the minimum is your lowest y value. And your maximum is your highest y value. I just want to stress that before we move on to this example. Okay, here's some examples. Okay, so here we want to find any maximum or minimum values of the following quadratics. So let's say I'm given a quadratic that's, let's say, x squared minus 4. Okay, you could even graph this and see what the maximum and minimum values are. So here, what I have to note is that I need to find my vertex, at least the x value first. So let me go ahead and find my vertex. What is the easiest way to find the vertex here? Well, this is in vertex form. If you think about x minus 0 quantity squared minus 4. So my vertex, I wouldn't have to use my formula. I could just say it's 0 comma negative 4. Okay. So my minimum or maximum value will depend upon whether it opens up. What's the opening here? Well, a is equal to positive 1, so it opens up. It opens up, and my value, if I think about this, it opens up, I will have a minimum. So I'm going to have a minimum which is equal to the y value of the vertex. So this graph right here is at negative 4. So this is negative 4, negative 3, negative 2, negative 1. Right here. My minimum is equal to negative 4 in this case. I can sketch it out. My sketch is not the best here, so let me emphasize this. 1, 2, 3, 4. Here's my negative 4. So that would be the lowest point of this quadratic. I have a minimum that's negative 4. One more example. In this next example, going to have f of x equals 6 minus 2x minus x squared. Okay, here I have another quadratic function, but this one I could see is not in standard form, and it's not in vertex form. Probably the easiest thing here to find the minimum or maximum value is to first find the vertex through your standard form, your formula. So if I rearrange this stuff, I have f of x equals minus x squared minus 2x plus 6. So this minus 1 right here is my a value, and my b value is minus 2. Okay. So what I want to do is find the vertex the x value of the vertex. You don't need to find the whole thing unless I really want to. Here I just want to find the maximum or minimum, so I could condense my steps a little bit. So find the x value of the vertex. And then what I want to do with the x value is figure out what the output is to find the y value. So I guess I do need both. So let me backtrack here. So the x value of the vertex is going to be h. X equals h, which equals negative b over 2a. So here that will be negative of negative 2 over 2 times negative 1. Okay. So that would be 2 over negative 2, which equals negative 1. So the x value of my vertex is negative 1, and then the y value, then y, which equals k, will equal f of negative b over 2a. And in this case, since I have f of x equals negative x squared minus 2x plus 6, then I'll have f of negative 1 equals negative 1 squared minus 2 times negative 1 plus 6. So this will equal negative 1 plus 2. So negative 1 plus 2 will give you plus 1 plus 6, which would be 7. Okay. Double checking my work here. Negative 1 plus 2, 7. Good. Okay, so my vertex altogether is going to be negative 1, 7. I have my vertex. Now I want to use that to find my minimum and maximum. So going back to what my problem's asking is, what's my max or min? Well, I could only have one or the other. And whichever it is, whether it opens up or down, it's going to be the y value of the vertex. So what I want to look at here is my opening. And since A is equal to negative 1, that means it opens down. Okay. So if it opens down, we have this. It's expressive of an object like in projectile motion that goes up and comes back down. That is a kind of curve that has a negative in front of the x squared. So it opens down. So in this case, I know I'm going to have a maximum. This means I'm going to have a max. I only have one or the other, so I have a maximum. And my maximum value will be is equal to 7 here. That's my maximum value. So that's how you find minimums and maximums. As you can see, everything depends upon previous steps. There is a lot of weight in finding your vertex correctly. If you don't have your correct vertex, you cannot get a correct axis of symmetry or a minimum or maximum value. Okay, so what we'll do is come back and look at graphing some of these and identifying all these properties. So we're going to take a look at how we can apply these properties to graphing quadratic functions. A lot of what we did here, like finding the axis of symmetry, finding the vertex, finding minimum maximum value, will really help in identifying the main properties of your graph. And then also what we're going to add to our graphs are x and y intercepts, and that will allow us to make some really good descriptive graphs of our functions. And then we'll look at some applications. So I hope this little algebra lesson outside is helpful to you, and we'll come back with more examples of doing all the different properties together. Thank you.